Good afternoon everybody, and welcome to laptop repairing online course. I welcome all my students from around the world who have joined this course, and I would like to make this course as interesting as I can, and I will be giving some specific information about component laptop motherboard repairing as well as deeper analysis of signal level repairing. In the very first class, I'm going to just give a brief idea of how a notebook motherboard operates, and we must note one point, that we are trying to repair a device which is made by a man. So everything that is man-made can be repaired if we know how exactly that device is working. And if you're trying to repair a thing that is made by God, it's going to be very difficult, and the job of a doctor is really difficult. But here we are trying to repair a notebook motherboard, and this is made by people like us. So we must note one very important point, that to repair electronic devices you must know the various connections present on that electronic device, and laptop schematic is that thing. Laptop schematics gives entire connections present on a notebook motherboard between the various chips present on the notebook motherboard. So in the very first class I will be covering the block diagram of laptop, and in this entire course I will be taking two notebook motherboard as a reference. One I have chosen the very famous model Lenovo G570, and equally famous HP DB2000. Lenovo G570 is an i3 based motherboard, whereas HP DB2000 is a dual core based motherboard. So I would be discussing what are the similarities between the two of the boards, and what are the differences between two of the boards, because nowadays we are getting i3, i5, i7 boards. So it's very important that we focus more on those kind of boards. But still, the dual core and the core 2 duo boards are in the market, so we must take both of them. So let's go into the schematic diagram of both of them. This is schematic diagram of HP DB2000, and this is a schematic diagram of Lenovo G570. As you can see, in HP DB2000 schematic diagram, the very first page of any schematic diagram describes the block diagram of that notebook. This is HP DB2000 schematic diagram. You can see this is Intel CPU, and this is a crystalline, which is an Intel terminology for GMCH, and this is Intel ICH8 Southbridge. We also call it as Southbridge, we call this as Northbridge. And inside this CPU you must notice one thing, it's written 4, 5 and 6. That means anything about this CPU is inside these three pages: 4 page, page number 4, page number 5th and page number 6th. So anything about this CPU connections are in these 3 pages. Inside this CPU we are saying one term, FSB. What exactly an FSB is? FSB means front side bus. So between CPU to GMCH we have front side bus, and this front side bus has 3 connections: address bus, data bus, control bus. FSB, front side bus. This has 3 parts: address bus, control bus, data bus. And the CPU has 2 kind of speeds. One is its internal speeds, which may be around, this is dual core board, so it will be around 1.8 gigahertz, and it has an external frequency, which is frequency speed of FSB, the front side bus. This is the speed at which the CPU processes data, transfers data between CPU to GMCH, while it has an internal frequency which is much higher. That means it can calculate data at a much higher speed, but it can transfer those data at a slower speed. So this is FSB. FSB is front side bus. Inside this GMCH, we are finding it's written as integrated graphics, LVDS and CRTs. GMCH is a graphic media controller hub, and it actually has two parts. One is display controller, another is memory controller. Display controller is for processing graphics. That means it has LVDS and CRT. If this NVIDIA graphic chip is not present, then the connection of CRT LCD TV out will be through this chip. Why we use NVIDIA chip is another question, but here just for reference sake I'm explaining it. We require NVIDIA graphics or ATI graphics for graphic intensive purpose, whereas the graphic intensive application requires parallel processing, and this graphic chip, they have GPU core, graphic processor unit, so they can process those graphic intensive application very easily. But this GMCH has an integrated display controller. That's why it's written LVDS and CRT. And you can see there are two slots, slot 0, slot 1 for DDR2 RAMs. These are slot and there, so data RAM, there are RAM on this slot, but the memory controller is inside GMCH. So data processing, anything memory processing is to be done by this GMCH, and it will give its output at the slots. So if we want to check the working of this GMCH, we have to check at the slots, at the connectors. Schematic diagram describes the various connections and interconnections between components present on a notebook motherboard. If we know those various interconnections and the working of those components on a notebook motherboard, we would be in a very good position to repair the board smoothly, and we would be loving our work of repairing. If you do something in a hit and trial ways, you get fed up. You get fed up when you do not solve that problem. But when you do step by step, when you do in an actual way, that thing is moving, and even if you don't repair things, then you are satisfied that you have done 100% of the job. 95% cases on a notebook motherboard can be repaired. Some 5% cases cannot be repaired because there are internal damages on a PCB board. So those cases, we are not going to discuss those cases. There are various steps to follow those cases, and I will explain those various steps at the end of the course. Right now we must concentrate on how exactly things on a notebook motherboard work. So you must know the exact schematic diagram, exact working of various components present on a schematic diagram. In simple manner, we must understand schematic diagram completely. This is schematic diagram of HP DV2000. I have already told, and I have emailed to all my students these two schematic diagram, HP DV2000 and G570. So I would urge my students to kindly open those schematic diagram as I would be explaining the things in this schematic diagram. The very first page of a schematic diagram explains the block diagram of a notebook motherboard, and in this first page, this is the block diagram. In the block diagram, you can clearly see this is Intel CPU, this is crystalline, which is Intel terminology for GMCH. GMCH stands for graphic media controller hub. This is NVIDIA graphic chip. As you can see, this is written Parme's discrete block diagram. Wherever this term discrete is, you must note discrete means this board must be having and graphic chip. Maybe it's NVIDIA graphic chip, or maybe it's ATI graphic chip. And if it's written UMA, then this is without graphic. That means the graphic capability of this GMCH would be used in that case. As you know, a GMCH, it has two portions: memory controller and display controller. Memory controller does the work of memory controlling between the RAM slot and the GMCH and the processor. Basically, this GMCH acts as an intermediary between the CPU and the RAM. As you know, router, if you look at, I'll give an example of networking. In networking, we use a router to route various addresses. Similarly, GMCH, it routes all the addresses from the CPU to the RAM. And I'll discuss this memory mapping. We call it memory mapping, how the various component on a notebook motherboard is mapped with CPU, how the CPU determines that the ICH is present at this address, the CRT is present at this address, the IO controller is present at this address. This is called memory mapping, and I will be discussing the system address memory mapping in a different class. Right now, we should note just two things: that GMCH stands for Graphic Media Controller Hub, and it has two parts. One is display controller for transferring display to the output. The output may be CRT, LCD, TV out as video. For LCD we have LVDS connection, and for CRT we have VGA connection. So display controller, it has got two parts. Display controller, if a graphic chip is present, then the graphic calculation processing would be done by this graphic chip. If it's not present, then the internal capability of the GMCH would be used, and in that case you cannot run graphic intensive application. Because why? A natural question arises, why we cannot use a graphic intensive applications? Because a graphic intensive application requires use of parallel processing of graphics, and this NVIDIA graphic chip, they have GPU, the graphic processing unit, which processes the parallelly. So this has got two connections, one the display controller and the memory controller. As you can see, there are two slots, slot 0, slot 1, two channel, channel A, channel B. The memory controller drives data at the RAM. So if you want to test this controller, as you know, this GMCH is a BGA chip, ball grid array. There are no pins across this IC, so you cannot test a BGA chip. You can only test a BGA chip at its output, at its connector. So these are connectors, these are controlled by their controllers. Connectors controlled by their controller, and the controller are present in this. This memory controller controls the output at this slot. The display controller control output at this slot, at this connector, CRT, LCD, TV out. Alright. So, and this is ICH8, which is also called South Bridge. This is primarily, its primary function is to coordinate with these sections: the new card, mini card, IO controller, HDD, that is hard disk, ODD, that is PATA disk drive, and USB, Bluetooth, camera, HD audio, and RJ45 connections. Alright. Okay, I think I'm very much clear with what I have spoken till now, and I will repeat once again. As we have spoken that the schematic diagram explains the various connections, and on the very first page of schematic diagram we have block diagram. Block diagram basically describes everything on a notebook motherboard in small blocks. As you see in this notebook motherboard, we have one processor, Intel processor, and you see this is 4 comma 5 comma 6. That means the entire connection of this processor is described in these 3 pages. Between CPU to GMCH we have a connection, host bus. You know what is bus is? Bus is a series of wires connecting these 2 chips, and there are various kind of buses present on a notebook motherboard. Between Intel CPU to GMCH we have FSB. FSB means front side bus, and it consists of 3 lines, 3 kind of wires, 3 kind of connections: address bus, control bus, data bus. Whereas between GMCH to NVIDIA we have PCI Express 16. In earlier kind of board we used to have PCI, not PC Express. What are the differences between these 2 kind of connections? I have just briefly mentioned those differences. PC Express is a newer version of PCI. PCI was basically a parallel technology in which many devices can be connected through same set of wires, thus dividing the speed, whereas a PC Express is a point-to-point connections. That means a different PCI is between GMCH to NVIDIA, a different PCI is between ICH to mini card. We are not sharing the same PCI. Whereas in PCI, the PCI lane can be shared between multiple devices, and thus speed is greatly reduced. Whereas in PC Express the speed is very high. As you can see, how many wires PCI Express 16 correspond to in a notebook motherboard. We'll check it out. Let's go into the pages of GMCH. 7 number. I'll zoom this and let's check where this PC Express connections are. Let's go to the next page. No, we're not finding, so let's go to the next page, and yes, here you see PC Express graphics. As you can see, there are peg underscore RXP15, peg underscore RXN15, alright, and this is peg underscore TXP15, and this is peg underscore TXN15. That means 2 wires for transmitting, 2 wires for receiving. RXP receiving. RXP means receiving positive, RXN means receiving negative. That means we have 2 wires for receiving and 2 wires for transmitting. TXP means transmit positive, TXPN means transmit negative. Why there are 2 wires for transmitting and 2 wires for positive for receiving is a deeper question. But I would just say that there are 2 wires because we don't want noise while communication between 2 electronic chips. We don't want those noises. That's why we have 2 wires. So PC Express 1 means 4 wires, 2 wires for transmitting, 2 wires for receiving. This is PC Express 16. That means there will be 64 wires between the GMCH and the NVIDIA chip. This is PC Express 16. That means there will be 4 wires. PC Express 1 means 2 wires for transmitting, 2 wires for receiving, whereas this is PC Express 16. So we would have 64 wires, right? 64 wires, 16 into 4, 64 wire physical connections between the NVIDIA and the GMCH. This is DMI. DMI stands for direct media interface. This is a dedicated connection between GMCH and ICH. ICH stands for input output controller hub, and in this block you are seeing ICH 8. ICH 8, there are various series of ICH. ICH 1, ICH2, ICH3, ICH4, ICH5, ICH6, ICH7, ICH8 till ICH10, and after that we have PCH. PCH is peripheral controller hub. This ICH is at the center of power management in a notebook motherboard. That is, it is responsible for the turning on and turning off of a notebook motherboard. ICH8 in conjunction with IO controller is responsible for starting on and starting off of a notebook motherboard. You can see between ICH8 and this is card reader, there is a PCI. PCI is peripheral connect interface. This is not PCI Express. Between ICH8 to audio controller we have HD audio. HD audio stands for high definition audio, and this is mini card. This is PCI Express 1, that means there would be 4 wires between them. And this is IO controller. IO controller, this is the first IC to be turned on a notebook motherboard. That means how a notebook motherboard start? First IO controller is start, then BIOS, then ICH, then GMCH, then CPU, and then clock generator. Clock generator is at the last. So you can judge, if clock generator is not working, then the notebook motherboard would be turned on, but it would be in no display condition, right? It would be in no display conditions because all the chips have already turned on, but they are not processing. They are not processing data. Data processing will start only when clock generator will get turned on, right? They are just on. They have just received their power, but they are not processing data. They'll process data once the clock generator drives clock signals to CPU and to all other devices. Alright, and on this page you can see various regulators present on the notebook motherboard. In this notebook HP DB2000 we have TPS 51120. This is 3.3 5 volt regulator IC. That means anywhere you are getting 3.3 voltage, it will ultimately come through this regulator. You have this MAX 8743. This is 1.05 volt regulator IC, 1.8 volt regulator IC. This is 2-in-1. It is generating 2 output with 1 input. So anywhere you are getting 1.05 volt, it would be ultimately coming from this IC. So we must not get confused. There are just 5 regulators on this motherboard. 1, 2, 3, 4 and 5. So there are only 5 power source on a notebook motherboard. So if your motherboard is dead, we have to check all these 5 power sources, whether they are getting turned on or not. If they are getting turned on, all 5 of them, that means the notebook has received its power. Alright, the notebook has received its power. So in this notebook motherboard we have only 5 regulators. So we have described the very first page. As you see, this is the very first page, block diagram, Pamir discrete. As I've told you, discrete means this notebook motherboard is having graphic. If it's written UMA, this notebook motherboard is not having graphic chip, and this is using the core capabilities of GMCH. IO controller controls touchpad, internal keyboard, thermal management and fan controller. CIR stands for consumer infrared. TPM is trusted protection module. What this is trusted protection module we'll discuss while we are discussing the IO controller. This is actually a protection mechanism. Like your laptop is lost, then this is a kind of protection mechanism. We'll discuss later on. So in the very first page, I think I have explained everything on this page, and we'll just revise once more. Like this is, we have discussed the block diagram of HP DB2000. And now after this, I will be discussing the block diagram of an i3 based motherboard G570, and in that board we'll see what differences are in the current i3 board. Okay, so we have till now discussed a schematic diagram of a dual core based laptop, that was HP DB2000. Now we'll concentrate on a newer kind of laptop. This is Lenovo G570. I must mention one thing, that whatever I'm explaining is common to all notebook motherboard. That is, when I'm explaining Lenovo G570, the concept, the signal name is common to all i3 based laptop. When I'm discussing HP DB2000, the concepts are very much similar in all kind of dual core based laptop. Maybe the position may differ, but the signal name would always remain constant. The concept is same. I'm just taking this two notebook motherboard as a reference case because I cannot take each notebook motherboard separately. So we can apply these concepts, we can apply all the things we are learning over here in all kind of notebook motherboards. So let's take this case of Lenovo G570. As I said, the very first page of a schematic diagram describes the block diagram, and if we understand a block diagram properly, we understand the entire schematic diagram. You see here it's Intel Sandy Bridge. What exactly Sandy Bridge is? Intel released various versions of its i3, i5 and i7 processor. The first version of i3, i5 and i7 processor were called Nehalem processor, and that were 45 nanometer technology. This is the manufacturing technology. After that, Intel releases second generation, which is called Sandy Bridge, and that was 32 nanometer technology, much faster than the Intel first generation. And Intel again releases third generation processor, which is called Ivy Bridge, and that is 22 nanometer technology, which is much faster than Sandy Bridge. So we get to know what exactly Sandy Bridge is. Sandy Bridge means second generation i3, i5 and i7 processor. That means if we place even a second generation i3 processor or second generation i5, it will run very well, right? There is a very confusion in the market that i3 means 3 cores. No, i3 doesn't mean 3 core. The Intel first generation i3, i5 and i7 are all dual core based. After that, 2 and 3 cores are present in the processor. That means dual core and Intel first generation processor are same. There are two cores inside them, right? Am I clear? i3 doesn't mean 3 cores, i5 doesn't means 5 core, i7 doesn't mean 7 core. Why this 3, 5, 7 are? This is basically according to the features. 3-star rating, 5-star rating and 7-star rating. You can just see this like this. You can see this 3, 5, 7 like this. There are 3 features, 5 features and 7 features. It doesn't mean 3 cores, 5 cores and 7 cores, right? Intel Sandy Bridge is second generation Intel i3, i5 and i7. That means if you place i3 second generation or i5 second generation, this board will work perfectly, right? In the HP DB2000 schematic we have seen, you see over here there are 3 chips: CPU, North Bridge and South Bridge. Here you are seeing just CPU and PCH. PCH means peripheral controller hub. Here there are no North Bridge and South Bridge. As we mentioned in a DB2000, GMCH consists of memory controller and display controller, right? Here the memory controller has moved to the processor, right? and the display controller is inside this PCH. Intel Cogger point. Cogger point means there are various versions of Intel PCH. If you go into the chip number, we have BD82HM55, we have BD82HM57, we have BD82HM65, 67, 75, 76, various version of PCH. Similar to ICH, we have ICH1, ICH2 till ICH10. In PCH we have BD82 HM55, 57, 65 till 76. So there are various versions of PCH. So one important thing we must note over here is the memory controller has moved inside this CPU, whereas the display controller is inside PCH, right? And one more important point to note over here is the graphic chip. This is discrete, right? This notebook motherboard is having graphic chip. So this graphic chip is connected directly with processor, right? And the RAM slots are connected directly with processor, because as we told, the memory controller has moved to the processor and the RAM slots are connected to memory controller. You see over here in HP DB2000, this is GMCH, it has memory controller and display controller. So the RAM slots are connected to the memory controller, right? But the question arises, why this graphic controller is connected to the CPU? Because our display controller is in PCH. So why the heck this display controller is connected to CPU? This is a very important change in the Intel architecture. Intel has kept the display controller in PCH, but it has kept the graphic processing unit inside CPU, right? So if your notebook motherboard is using an external graphic chip, then in that case the connectors HDMI, CRT and LVDS are connected to the graphic chip, and there is a two connection between the CPU, the FDI. FDS stands for flexible display interface and DMI stands for direct media interface. So if a notebook motherboard is using an external graphic chip, then in that case the display would be controlled by this graphic chip and this FDI won't be used. FDI means flexible display interface. Let's discuss into more detail. You see over here the CPU, we have the display. Actually there are two terms that we need to discuss. There are display planes and display pipe, right? So Intel has kept the display controller in PCS, the output controller, right? LVDS, HDMI and VGA controllers are in PCH, but the graphic controller, the GPU is inside CPU. The GPU unit is inside CPU, and there is a EDP, embedded display port. This is a new technology. As you see in the LVDS, it has a larger number of wires. LVDS stands for low voltage differential signal, whereas EDP stands for embedded display port, and it has a smaller number of wires. So if there is a connection between LCD screen and EDP port, there is a less number of wires, that means less number of noise, and that means better quality of picture. Whereas in LVDS, low voltage differential signal connection, you have larger number of connectors, so there is a possibility of noise, there is a possibility of lower quality of image. So what we are discussing is FDS stands for flexible display interface, and this is dedicated only to transfer of graphic data between CPU and PCS. That means if this notebook motherboard is not using graphic chip, then the graphic data would be transferred between CPU to PCH via this FDI, flexible display interface. And if a notebook motherboard is having external graphic chip, then this FDI won't be used, right? In that case, the output connectors, they are directly connected to the graphic chip. Alright. And DMI, as we know, DMI, you check here in DV2000, it was a dedicated connection between GMCH and ICH. And here, as we said, the memory controller has moved to the CPU. So there is a connection between the CPU to PCH DMI, direct media interface. This is for transferring of data between CPU and PCH except the graphic data. I must mention except the graphic data, because for graphic we have FDI, flexible display interface. So the basic difference between Intel dual core architecture and i3 based architecture is RAM is directly connected to CPU. The graphic chip, external graphic chip, is directly connected to CPU. That means we have now a lesser number of intermediaries between CPU to RAM. There is a direct connection between CPU to RAM. That means it would be much faster than a dual core. Similarly, the graphic is directly connected to CPU. It would be much faster for graphic processing unit. And we have lesser number of big BGA chips on notebook motherboards, so it's very easy to repair a i3 based and i5 based notebook motherboards, because there are less number of BGA chips present on these motherboards. So very important points we have already discussed is FDI is flexible display interface, and the PCH has display controller, and it would be used only when this is not present. Alright. And between PCH to IO controller we have LPC bus. This is low pin count bus, and similar to the DV2000, this is written 5 to 11. That means the processor is described between page number 5 to page number 11. As you see, DMI EDP, as I said, EDP is an embedded display port. This is a newer technology, much advanced than the LVDS technology, ensuring less number of wires. That means ensuring a better quality picture. Let's go back to page number 1 again, and we must again discuss the very important points between an i3 and a dual core based motherboard. In i3 based motherboard, the RAM and the graphic chip are directly connected to the CPU, whereas in a dual core based motherboard, the RAM is connected to the GMCH and the graphic is connected to the GMCH. Alright, and we have a DMI connection between the CPU to the PCH. So there are two kind of connection between the CPU to PCH. One is FDI, flexible display interface, only used for graphic transfer, graphic related data transfer, and DMI is the direct media interface. Except graphic media, the processor will use DMI. That means if processor want to interact through BIOS, SPI ROM BIOS or EC BIOS, then the connection would be, the data transfer would take place through this bus, DMI. Let's check FDI, FDI into 8. Let's check what does it mean. Alright, so let's go to page number 5. FDI. I'm not finding in this page, so we'll go to the next page. Next page, and we'll discuss all these pages in explicitly manner. Very explicitly we'll discuss all the connection very explicitly, because understanding this connection will only give insight on how to repair a problem. So we are going to check FDI connections. FDI is flexible display interface, a very important technology in i3 based motherboard. This is power unit, and as I say, the last page of any chip is power page. That means what I'm saying is between page number 5 to 11. So the last pages, the 11 page number or 10 page number would only describe the power pages. So we have to check the FDI connections between 5 to 10. FDI, this is DMI connection and this is FDI. Oh, the very first page is FDI. You see FDI into 8, right? FDI 0, FDI 0TX, FDI 0TX1, right? This is PRX N0, N1, N2, N3, N4, N5, N6, N7. This is P0. This is negative, this is positive. 0 to 7, 8. 0 to 7, 8. That means for each connection we have two wires. One negative, one positive. That means there are 8 wires. So FDI 8, that means 8 into 16. There are 16 physical wires between. There are 16 physical wires between the processor and the PCH for FDI. FDI into 8, right? And this is PCI Express 6, and this is connected to the LAN controller, SPI ROM, serial peripheral interface ROM, and this ROM consists of many kind of BIOS firmware like AMI BIOS, management engine BIOS, system BIOS, and EC. EC is responsible for touchpad and internal keyboard, as we have already discussed. And SPI ROM, this consists of EC BIOS, the embedded controller BIOS for the IO controller. LPC, low pin count bus between PCH and EC. This is same as we found it in dual core board. Agelia, Agelia means IHDA, Intel High Definition Audio. Alright, and this is bank 0, 1, 2, 3. That means there can be 4 bank, whereas you see in DB2000 this is only channel A, channel B. That means there are only 2 banks present on this kind of boards, right? So it can support 8 GB of RAM, right? This can support 8 GB of RAM. So I think I'm very clear with the description of this i3. The first page of this is schematic diagram and the first page is block diagram. Alright, so we have what are the major differences between a dual core and i3. In a i3 based motherboard, the memory controller of GMCS has moved to the CPU, whereas the display controller has moved to the PCH. The graphic chip and the DDR RAMs are directly connected to the CPU, ensuring more speed, whereas in a dual core based motherboard we have RAM connected to the GMCH and the graphic connected to the GMCH. So I think I'm very clear with the today's discussion and the today's class, and if you have any kind of problems or any kind of queries on what I've explained till now, you all can email me on my email ID, and I'm also online on Skype sometimes, so we can discuss those queries. And your feedbacks are very important to improve this course, and you can also email me what extra you want in this course, because I want you all to be a very good engineer and to earn more from your work. Thank you everybody. Welcome everybody. This is the second class of laptop chip level repairing course, and in this class I'm going to cover basic electronics, which is the framework for repairing any electronic device. In this class I would tell you about the exact working of an electronic components, and if we understand the exact working, testing is very easy. I assume that most of the audiences are pretty aware of the testing ways. But how this class is different is that here we will understand things, not remember things. And I have seen in the market around 90% of engineers that remember ways to test electronic components. If you understand the working, there is nothing to remember and you will love repairing. So let's go to the next slide. So First we'll discuss what is exactly electricity. Electricity is flow of current, flow of electrons in a wire, and there are three terms associated with electricity. One is voltage, second is current, and third is resistance. What is voltage? I think many people are confused with the voltage, current, resistance in a PCB or an electronic circuit. What exactly flows? I have seen that people assume that voltage flow. No, voltage is same as pressure. You know, water flows in a pipe. How water flows? It flows due to difference in pressure level. Similarly, current is flow of electricity, and how current flow? Current will flow due to differences in voltages. So voltage is similar to pressure of water, and current is flow of electricity. So current flows, never voltage flow, and current will only flow from a high voltage to a low voltage. So there should be a difference in voltage for flowing a current. And what is resistance? Resistance is any restriction to flow of current in conductor. You see here, resistance is any restriction to flow of current in a conductor, right? So there are three things to understand: voltage, current, and resistance. Voltage is similar to pressure, right? And current is flow of electricity. Let's go to the next slide. So as earlier I have discussed, voltage is pressure that is applied to the conductor, and there are two types of voltages: AC voltages and DC voltages. AC is alternating voltages and DC is direct voltage. AC voltage means it will vary, the direction will vary, whereas in a direct, the direction would be fixed. And AC voltage is generated by generators. You must have seen various kind of power station, the thermal power station and the hydel power station, where the armature moves. You see here over here in the figure, the armature moves and it generates a varying voltage, and we call it AC voltages. Whereas you have seen the cell or the battery, it has a fix, it is the fixed voltages, so we call it direct voltages. And one very important thing to note over here is, finally any electronic device, it will work on a direct voltages. So let's see an example of motherboard. In the motherboard, as I said, any electronic device will require, any analog device will require a direct voltages. So we must need any device which can convert the AC to DC. And we have an SMPS. In a desktop motherboard, we have SMPS to convert the AC voltages to the DC voltages, whereas in a notebook motherboard we have adapter which will convert an AC source to a DC source. Similarly, we have two types of current: an AC current, a DC current. In the AC current, the direction of flow of current varies, whereas in DC the direction is fixed. And the symbol for an AC voltage is C. This is the symbol of an AC voltages, whereas this is the VDC. This is a symbol of a DC voltage. So anywhere in the schematic diagram you find VDC, that means it's a DC voltage. And we must assume in a schematic diagram, if there is nothing mentioned, you should assume that this is a direct voltage, this is a DC voltage, because any electronic PCB or an electronic device, it finally work on a DC voltage. Resistance, as I said in the previous slide, the resistance is a restriction to the flow of current, and the symbol is omega. See, this is Ohm's law. So I think it might seem a little bit theoretical to the repairing technician, but this is not really theoretical. and the Ohm's law is the key of any electronic circuit. What exactly is an Ohm's law? I won't get into much detail over here because I assume my audiences are only focusing on the diagnostic skills. But to learn diagnostic skills, one must understand the underlying principles. So Ohm's law is basically the underlying principle behind any electronic circuit, the operation of any electronic circuit, and this is the relation: V voltage is equal to IR. I is current, or current is measured in ampere, so this is A, and resistance, this is omega, this is measured in omega. So this is a relationship between voltage, current and resistance. So if you increase the voltages, your current will increase, but if you increase the resistance, your current would be decreasing, because resistance is restriction to flow of current. So I think I am very clear with what I have told right now. I spoke about voltage, current and resistance, and one must not confuse between voltage and current. Voltage is similar to pressure and current is flow of electricity. So what flows in a circuit? Current flows in a circuit. Now let's go into electrical circuits. We have two kind of circuit. One is series circuit and one is parallel circuit. What exactly series circuit is? In series circuit, each device is connected together in a line, right? Current flows through each device connected to the circuit. That means, how do you recognize that this is series circuit, or how do you recognize that two resistors are connected in a series, or how do you recognize that two capacitors are connected in parallel? See, if you tell that two resistances connected in a series, it means the same current will flow across both of the resistance. And when I say two resistors are connected in parallel, that means same voltage is between both the resistance. Like here in the image, this resistance and this circuit, the switch, they are in series, whereas this resistance and this light, they are in parallel, right? Because there is same voltage across this resistance and same voltage across this light, whereas here in this case there is same current across this resistance and same current across this light. So how do we recognize a series circuit? In a series circuit, same current will flow, whereas in parallel circuit, the voltages across both the component would be same. Alright, let's move on to the next slide. And multimeter. See, multimeter is the device to measure all the values of voltage, resistance, current, and to test the various electronic components present on a motherboard. So we have two types of multimeters. One is digital multimeter and another is analog multimeter. In the digital multimeter, this is a digital multimeter, you will have an LCD display. Assume everybody is using DMM, the digital multimeter. They will have a LCD where the values will be shown, whereas in an analog multimeter you will have a needle which will turn according to the values, right? So when you are repairing a notebook motherboard or when you are repairing electronic device, nowadays we use digital multimeter because digital multimeter clearly shows the values, right? Digital multimeter. See, here in our lab we are using the CHP 208, which is manufactured by Tronik, and this is an auto ranging multimeter. By auto ranging I mean you don't have to set across you don't have to turn the knobs, right? It will automatically register the value. Like if it is in the range of 1000 ohm, or if it is in the range of 100 ohms, you don't have to turn the knob across that, it will automatically shows the value. So I suggest to use an auto ranging multimeter, and we divide multimeters into various categories according to the use. This category 4, this is a primary supply, overhead or underground utility service, so this is not for our purpose. And category 3, this is distribution level means and fixed installation. Again, this is not for our purpose, because the purpose is to repair a notebook motherboard or a desktop motherboard or a tablet. For us, we need a category 1 multimeter, and CHP208 is a category 1 multimeter, an auto ranging multimeter, a multimeter which can measure logic also. I'll discuss what exactly logic means, and how it can be helpful if we use a logic multimeter. Now, use of a digital multimeter. How exactly we use a digital multimeter? For using digital multimeter to test an electronic component, we have to first set the function. Like if you want to measure the resistance, you have to turn the knob across the resistance, and then you have to set the range. If you don't have an auto ranging multimeter, this is not an auto ranging multimeter, because you see values are written 200, 2K, 20K, 200K, 20M, whereas this is an auto ranging multimeter. Here you don't find those ranges. This multimeter will automatically adjust to give the right values. So the setting the range, the next step of setting the range is not at all required in an auto ranging multimeter. So thereby I suggest you to use an auto ranging multimeter. And DMM continued. These are the various symbols. This is for V and this is for AC voltage, right? And this is for DC voltages. These are the various symbols written on a normal digital multimeter. And this is MV means millivolts, and A means ampere, that is for a unit for measuring current, and milliampere, this is smaller current, and this is omega for measuring resistance, and this is for diode range. This is a very important utility present in a digital multimeter, and people are very much confused about when to use diode range and when to use continuity range. So I would also discuss that point, that when to use diode range and when to use continuity. Continuity is a simple procedure. This continuity utility is a simple procedure to measure the continuity between the circuits, right? Continuity between the circuits, or to measure the low resistance. And this is for capacitance. Measuring a capacitance is one of the big tasks, and you must know the proper procedure to exactly measure the capacitance. Otherwise you might land in some kind of accident, which I really don't want to. So we'll discuss the exact procedure to measure the capacitance. DMM continued, and I've already spoken about the types of multimeter. One is the manual ranging multimeter and another is auto ranging multimeter. Like you see, this is a manual ranging multimeter. You have to manually turn the knob to the exact place, the range of the values that you have to measure. And this is an auto ranging multimeter. You don't have to turn the knobs, you just have to set its function, like what thing you need to measure. Alright, let's go to the voltage measurement. As spoken, we have two types of voltages, AC voltage and DC voltage. So you have to turn the knob to what exactly you need to measure. Here, as I said, this is for DC voltage and this is for AC voltage. These are the symbols present on a DMM, a digital multimeter. So you should be aware of these symbols, and I assume most of the guys are pretty aware of these things. And if you are new to this line, you can refer this chart. You see, okay, this is an AC voltage and this is DC voltage. So I would be covering from very basic, and because I think many of my students are really a new entrant to this line. So if you feel any confusion or if you don't understand anything, I would always welcome queries from your side. So what exactly you have to measure? If you want to measure AC voltage or DC voltage, you have to turn the knob. Like here this is representing a DC voltage, and you have to put the red probe, that is the positive probe, into the positive side and the black probe into the negative side, and this DMM, because as I said, we will be using a digital multimeter, we want to be using an analog multimeter. So any test which I will be discussing in this class would be by a digital multimeter, not an analog multimeter. So this is digital multimeter for measuring AC voltage, which is very, very straightforward. There's nothing you have to do. You have to just turn the knob and you have to place where exactly you want to measure a voltage. And one thing you have to take care is we have to put the multimeter in parallel with the device across which we are measuring voltages, right? Because what I said, in a parallel circuit, these two devices would have same voltage, right? So if you want to measure voltage, we have to put the multimeter parallel to the device. All right. The current measurement, as I said, current measurement you can do it only if you put the multimeter in a series. Like here we have put the multimeter in a series, and it's really very difficult to measure current, because to measure current you have to basically divide this circuit and you have to then connect the multimeter to that circuit. So it's not advisable to measure current while if the circuit is on, right? Because in that case a very high value of current might enter into your multimeter and might damage your multimeter. So measuring a multimeter can be done by measuring a multimeter. Measuring a current can be done by two ways. One is clamp meter and another through normal multimeter. So really not advised to measure current. Measuring current is required when voltages at each of the specified location in a electronic PCB circuit is same, but your device is not operating in the right condition. In that case we have to basically observe the right current, whether which the electronic component is taking the right current, right? So I will not advise my technicians to measure current in that case. Or if you want to really measure current, then you have to use clamp meter. So never try to measure current with a normal digital multimeter, because the way I'm saying this is a logic. The logic is all the electronic PCB circuits are made keeping voltages to be fixed at a specified location, right? Current varies according to the type of work you are doing. Like if you are running a highly intensive graphic application on a notebook motherboard, in that case there will be requirement of use current. And when you are doing nothing on a notebook motherboard, suppose it is in normal state, data state, is not doing anything, in that case the current consumption by a processor is very less. So the value of current increases and decreases according to the application, the type of application you are running. So what exactly is fixed is voltage. So if we are going to diagnose any circuit, what you can measure, how you can diagnose a circuit? You can diagnose a circuit if you want to, you have to measure voltage, because voltage is always fixed. Whatever type of application you are running, voltage is always fixed. And as I said, we measure current when we find a situation where all the voltages are exactly coming, all right, but the device is not operating normally. In that case we use oscilloscope. We use oscilloscope to test the various signals, and I would be having an extra class on how to use oscilloscope, what things we really test and observe in a oscilloscope. All right, so in the next slide we go to the next slide, and the next slide is continuity measurement. What exactly continuity measurement is? Continuity is a quick check to see if a circuit is complete, right? Continuity is a way to check if a circuit is complete or not. Okay, so continuity measurement. Continuity is a very good utility present on a digital multimeter, and by this utility we can measure the completeness of a circuit, whether the two paths present on a circuit is same, whether these two devices are connected. We can judge it through continuity. So continuity basically is a quick check to see if a circuit is complete or not. So what happened in a continuity range? In the continuity range, the multimeter drives a small current across the path where we want to measure the continuity, and it measures resistance, and this resistance is displayed across the LCD. So if the student asks what exactly is the value present on a multimeter is, this value is basically the resistance across the path where we're trying to measure a continuity. And if this resistance value is less and an audible beep sound comes, that means that circuit is complete. This is also a very good way to test fuses and to test a closed switch. If across a fuse it gives an audible beep sound, then that fuse is good, and if across a switch it gives beep sound, that means that switch is closed. So let's go to the next slide, and in the slide this is resistance type. As we have already discussed what resistance is. Resistance is basically restriction to the flow of current, right? Restriction to the flow of current, and there are various type of resistors present. Carbon composition resistor, film or cement resistor, wire bound resistor, semiconductor resistor. It seems to be a little bit theoretical, but for knowledge sake one must know how many types of resistors are. And in the next slide we'll also see the film resistors, the wire bound resistor, and the SMD type resistors. This is very important, how to calculate the resistance through the colors present on a resistor, right? There are 4 colors. We have 3 type of band of colors present on a resistor. Some resistor have a 4 color present on it, some resistor have a 5 color present on it, and some resistor have a 6 color present on it. So we'll calculate the resistance. All right, so let's take the first case, the 4 band color code. As seen, this is the first color. So first color will represent the first digit. This is a brown, so brown, let's put over here 1. All right, this is black, so black is the second digit. Black means 0, so let's put 10, 10. All right, and this is orange. Orange here means 1k, so 10 multiplier, so we'll have to multiply 10 by 1k, that means 10k. And this yellow is basically tolerance, so this resistance value is 10k ohms plus minus 5%. And let's go to the second 5 band color code. The first color will represent the first digit. This is yellow, so it will represent 4, and this is brown, so violet, basically this is violet, so it will represent 7, 47. And we have green, so this is 475, because here this is 3 digit, because for 5 color code the first 3 colors represent the first 3 digit. So 475, 475 multiplied by red. Red is 100, for 475 into 100 plus minus, this is the tolerance, plus minus 1%. 475, all right, 475 multiplied by 100 plus minus 1% is same as 47.5 k ohms plus minus 1%. All right, you got it? Or you can also write this as 475 into 100 ohms plus minus 1%. In the 6 color code, the first three color represent the first 3 digit, the 4th color represent the multiplier, the 5th color represent the tolerance, and the 6th color represent the temperature coefficient. So let's calculate for it. This is red, red means 2, and this is violet, so it means 7, 27, and this is blue, so it means 6, 276, 276. This is multiplier, black, So we'll multiply with 1, that means 276, and this is tolerance to 276 ohms plus minus 5%, and this is temperature coefficient. Brown. What exactly is temperature coefficient? Is in physics, or we should also note over here, is that the resistance changes. Resistance changes due to the increase due to change in temperature. All right. Right, so basically resistance increases with increase in temperature for a normal electronic component, but for a transistor this is vice versa. There the resistance decreases with the increase in current, with the increase in temperature. All right, so not worried about the temperature coefficient, because from a diagnostic point of view we are really not worried about the temperature coefficient. But if you want to understand things, you must note that the resistance increases with an increase in temperature, whereas a resistance of a transistor decreases with an increase in temperature. Alright, so let's measure the resistance. And as I said, the measuring unit of resistance is ohms. So how do we measure a resistance? Through a multimeter. Alright, we can calculate the resistance through the color code present, but we can also measure the resistance through a digital multimeter. So as I said, there are two things. First, you need to set the function. So we have set the function, we have turned the knob across the ohms range, and we have the red probe to the one side and to the black probe to the other side, and it will display the value of resistance. And if the value of resistance is similar to the values calculated through the color coding, that means this resistance is good. This is good quality resistor. All right. Capacitor. A capacitor is one of the very if you do not understand capacitor, you will really confuse what exactly the capacitor does in electronic circuit. So we must be aware of what exactly is the working of a capacitor and why capacitor is used. Basically, capacitor is used to store electrical charge. All right, is used to store an electrical charge. Now the uses of capacitor varies when it is used in an AC circuit or when it is used in a DC circuit. When I mean DC circuit, I mean the input is DC, and when I mean AC circuit, I mean the input is AC. AC means varying voltage, whereas DC means direct voltage, fixed voltage. So let's understand this entire diagram. Capacitor, they are measured in farad, and they have basically there are two types of capacitors. One is fixed, another is variable, and the fixed are also divided into two ways. One is polarized capacitor and another is non-polarized capacitor. If the capacitor is a polarized type, then you have to connect the capacitor according to the polarity of the device. That is, the positive has to be connected to the positive side of capacitor, and the negative supply has to be connected to the negative side of capacitor. If you don't do so, then you can really create a mess. So you must note there are two types of capacitors. One is fixed, another is variable, and in the fixed type we have two types, the polarized and the non-polarized. Polarized are like tantalum and electrolytic capacitors, and the non-polarized capacitors are ceramic and paper types. And as I said, what exactly is the function of a capacitor? Capacitor is used to store electrical charge and then release current in the circuit in which it is connected. All right. And what are the application? You must see in the RAM modules, we have tiny capacitors present across that RAM. What they are actually used for? They are actually used for storing the charge. As we move on to the tracing, and I'll also discuss how exactly the capacitor work for, but for the timing, please note my following two sentences. In a DC circuit, when current is applied across a capacitor at time t is equal to 0, like suppose you have applied a capacity, you have a capacitor in a circuit and you apply a current flows through that capacitor, then initially that capacitor will allow the current to move across it, but with passage of time the capacitor will block the current. So at time t is equal to 0, the current will pass through that capacitor, whereas later on the capacitor will block that current because the capacitor gets charged, right? So this is a very good utility, right? Because the current will pass through the capacitor initially, but later on the current could not pass through it because this capacitor is fully charged. All right. And here also I have also written like a capacitor blocks DC and allows AC current. As I said, in a DC circuit, at time t is equal to 0, it will allow the current to move, but later on it will block that current to move. And if an AC current is moving across the capacitor, it will allow the AC current. So mark my two sentences. One that I have said is a capacitor in a DC circuit at time t is equal to 0. That means initially the capacitor will allow the flow of current, whereas at later time the capacitor will block that current, and the capacitor will always allow an AC current. We have these types of capacitor: electrolytic capacitors, tantalum capacitors, mylar, ceramic and polystyrene. And capacitors have a voltage rating. We call it working voltage, and basically this rating specifies the maximum voltage that can be applied across the capacitor without puncturing the dielectric. Alright, and as I said, a polarized capacitor must be inserted in proper orientation with respect to the applied voltages, whereas you can place the non-polarized capacitor in any orientation. Capacitance calculation. Here this is 102K. Alright, the first digit represents the first significant digit, the second digit represents the second significant digit, and the third one represents multiplier, where the fourth, that is alphabet, it represents the tolerance. So how would we calculate this capacitance? We can basically, these are for a non-polarized capacitor type. All right, these digits, this kind of digits are written on a non-polarized capacitors. So let us calculate 1 0, these are the first two digits. All right, and 2 is the multiplier. So 10 into 10 to the power 2 plus minus K, 10%, that means 1000 picofarad plus minus 10%. By this way we can calculate the capacitance of any non-polarized capacitor where some 3-digit value is written. Alright, I'm okay. I think I'm okay. Like how to calculate the first two digit. This is first digit, this is the second digit, the third digit is the multiplier, and the last alphabet is a tolerance. So 10, 10, 2 is the multiplier, that means 10 into 10 to the power 2, that means 1000, and picofarad. All these capacitance are measured in picofarad. Alright, and K is the tolerance. Tolerance means plus minus 10%. Tolerance means if the capacitance, that is, if the circuit requires 10% more than this capacitor, even though this capacitor can be used, and if the circuit demands 10% less than this capacitance, even though this capacitor can be used. Alright, so how can we test a capacitor? Now this is the very good question. How to test a capacitor? If you understand my earlier two sentences, you can really test a capacitor. To test a capacitor, what I have spoken. I have spoken that in a DC circuit, a capacitor will allow the current to move across it initially, and it will block the current afterwards. That means initially the capacitor offers less resistance to the flow of current, and after some time the capacitor will provide an infinite resistance because it will block the flow of current. So if we understand the working of a capacitor, we can test a capacitor. So as spoken, at initially the capacitor allows the current to move across it, whereas after some time the capacitor blocks current. So what it basically means is the capacitor provides less resistance initially, and afterwards it will provide an infinite resistance. So if we want to test a capacitor, the first very important thing that we have to do is we have to discharge the capacitor, because capacitor stores charge, and if you do not discharge, then it will create mayhem. Yes, it can create mayhem. So you must discharge that capacitor. So as spoken, we will test the functionality of this capacitor. So will the red probe, that is the positive probe, to the positive side, and the common probe to the negative side or to the other side. So at time t is equal to 0, the multimeter in the, as I said, in continuity range, what happens in continuity range? The digital multimeter drives a small current. So this small current will move across this capacitor, and resistance is measured over here. So this capacitor will provide less resistance initially, but after some time it will go to infinite resistance. Infinite resistance means 0L, that means open line. OL means open line, that means infinite resistance. So if initially it gives less resistance and after some time it goes to OL, that means this capacitor is good. You understand the values present over here? As I have spoken that initially capacitor will allow the current to move. That means the capacitor will give a less resistance to the flow of current initially, but after some time it will give infinite resistance because it blocks the flow of current. So in the continuity range it will give you less resistance initially, and after some time it will give you OL. Alright, but the best way to measure capacitance is this procedure is only when you remove out the capacitor from the circuit. When you remove out the capacitor from the circuit, you have to remove at least one leg of the capacitor. But if you want to measure the capacitance, you don't want to remove that capacitor. In that case, this is failure. This process is failure. In that case, you have to use an ESR meter. ESR stands for electrostatic series resistance. Electrical series resistance. All right. ESR stands for equivalent series resistance. All right, I was wrong. Basically, ESR is equivalent series resistance. So if you want to measure a capacitor by not removing it from the circuit, then in that case you have to use an ESR meter, which means equivalent series resistance, and this is particularly used for testing the electrolytic capacitor. And the best ESR meter in the market, or this is Mastec brand, Mastec LCR tester. This is MS5308, a little bit expensive, but this is a very good ESR meter, and this is quite applicable when you do not want to remove the capacitor out of the board, and you have to measure the capacitance, whether this capacitor is good or not. In that case you have to use an ESR meter. But if you want to check the functionality of a capacitor by removing it, then a normal digital multimeter is very good, and you can use it, digital multimeter. If you want to remove that capacitor and then measure it, then this is a good way. But if you want to measure the capacitor, if it is on the circuit, then do not use this process. Always use an ESR meter, because ESR meter is equivalent series resistance. Alright, I won't go into much detail what exactly is an equivalent series resistance. This is bit more theoretical over here, so let's not go into the theoretical and let us serve the purpose of diagnostic with the right concepts. Okay, so I think till now we are very much clear with resistance, capacitance, and the process to measure the resistance and to check the capacitance. Alright, so let's go with inductor. You can call it inductor as quite opposite to the working of a capacitor, because inductor is basically an electrical device which is having wires across it. You see these are wounds, wire wounds, okay. And what exactly is the working of this inductor? An inductor opposes the change across it. That means if we apply a voltage source across this inductor, then a current will flow, but initially this inductor will oppose the current, but later on this inductor will become like a wire that will assist the flow of current. So this is exactly opposite to the capacitor, because for the capacitor we said it will allow the flow of current initially, but it will block current after some time, whereas in inductor it will block the current initially, but it will allow the current after some time. So it is exactly opposite the working of a capacitor. All right, and an inductor blocks AC and allows DC, whereas a capacitor blocks DC and allows AC. All right, as we have checked over here. So how do we check an inductor? Basically in inductor we check the continuity of these wounds of wire, and for continuity we know we have to check across the continuity range. So across the continuity range it will give a very less resistance. That means these all wires are connected. So checking an inductor is very pretty easy. We can use it across a continuity range, and it will give you very less value and also a beep sound. All right, so this is the way to check a inductor. But we must notice important difference between a capacitor and inductor. Inductor will block the flow of current initially, whereas it will allow the current after some time, and a capacitor will allow the current initially and block the current after some time. All right, and we'll check this working in this circuit. Here you might be getting confused, but just notice my points on which I'm giving a stress. I'm giving a stress on the working of capacitor and inductor. A capacitor allows current initially, blocks current after some time. Why it blocks? Because it builds charge across its plate, right? So it will block the current after some time. An inductor, as I said, inductor opposes the change across it. So if you are trying to move a current across it, it is a change. So inductor will block the change. Inductor will oppose the flow of current initially, and after some time it will assist. So this is exactly opposite to the working of capacitor. Let's move on to the next slide. Diode. Diode is a very important semiconductor device present on any electronic PCB circuit. Let's understand what exactly is a working of a diode. Diode is a semiconductor which will allows the flow of current only in one direction, right? It will allows a flow of current only in one direction, and we can test. I won't go into much detail, but I'll just specify what is exactly forward bias and what is exactly reverse bias. As we know, a diode has two junctions, PN junction. We call it PN, one junction, PN junction, P side and N side component. P side means that that component is having a lot of holes present in it, and the N side component means that that side is having more of electrons present in it. So a diode has a PN junction, and forward bias means the P side should be connected to the positive power supply and the N side should be connected to the negative power supply. So in this case, this diode is a forward bias. Forward bias means PN P means positive, so positive should get connected to the positive power supply, and N means negative, so it's get connected to the negative supply. And a diode will allow a current only when it is a forward bias. So note my points. A diode will allow a current to move only when it is forward bias. Here you see the P side in the next image. You see the P side is connected to a negative supply and the N side is connected to a positive supply. So this is a reverse bias, and a diode won't allow a current to move across it when it is reverse bias. How do we check a diode? And a digital multimeter has a very good utility present in it, that we call it diode range. But people are very much confused. What exactly is displayed onto the LCD display when we are measuring diode? Basically, in the diode range, the diode range measures the junction potential between the PN, junction potential between the P side and the N side. So the diode range measures the junction potential. So if the value displayed is between 0.5 or between 0.5 to 0.6, then this diode is okay. All right. When you forward bias a diode, so what are the testing procedure for a diode? You have to attach the positive of the DMM to the P side and the negative probe to the N side, and if the value is displayed is between 0.5 to 0.6, then this is good. And in the reverse side, if the value displayed is 0L, that is overload, then this diode is good. So what exactly we are measuring over here? We are measuring the proper working of a diode. As I said, a diode will allow a current to move across in a forward bias, and it won't allow a current to move when it is in reverse bias. But this diode range, there is a very confusion. The value present on the LCD of DMM in the diode range does not represent resistance. Kindly note, because people are confused with this. The value present on the LCD in the diode range is junction potential, and this is a very good utility only present in a digital multimeter. So as I said, if the diode is good, then the junction potential in a forward bias will be of value ranging between 0.5 to 0.6, and in the reverse bias it will be 0L. This is not resistance, this is junction potential. Here the diode range is giving the value of junction potential, not the resistance. Transistor. Well, we have two kind of transistor. One is the bipolar junction transistor and another is field effect transistor, also called as MOSFET. And transistor, the BJT, the bipolar junction transistor, is divided into two kinds. One is the PNP and another is NPN. Basically, transistor have two junctions present over here. In the previous slide, we see the diode, they have only one junction, the PN junction, whereas in the next slide you see a transistor has two junctions, PN and NP. So bipolar, why they are called bipolar? Because the control current must go through two types of semiconductor material, the P side and the N side, and the current can be of two types, one having the flow of holes and another having flow of electrons. So this is called bipolar junction transistor. And as said, there are two types of bipolar junction transistor, one is PNP and NPN. How do we recognize what is which one is PNP and which one is not PNP? Through the symbol PNP. P means pointing in, so this is pointing in, so this is PNP. NPN means not pointing in, so So this is not pointing in, this is pointing outside, not pointing in. So this is an NPN. And they have this transistor, they have three kind of leads present on it. One is collector, another is base, and another is emitter. Why transistors are called transistors? Transistor basically means transfer of resistors, and the basic working of a transistor is it amplifies the small current present on the base to a high current flow between collector to emitter. All right, see my point. Transistor function as a current regulator by allowing a small current to control a large current. Like here, if we control the current at the base, we control the current flowing from collector to emitter. All right, a small controlling current and a large controlled current. This is PN, not pointing in, right? This is pointing in, this is PNP, this is not pointing in, this is NPN. So small current, there is a small current at the base, and this is governing a large current. So basically transistor can be used in various applications. It can be used as a switch. It can be used as a switch. It can also be used as a current regulator, because a small change in base current can result into a very high change in collector emitter, between the current flowing from collector to emitter. All right. So in order to for a transistor to function as a current regulator, the controlling current and the control current must be in the proper direction. I mean, proper directions means the emitter current is equal to collector current plus base current in any type of transistor. Here this is PNP, pointing in transistor. All right, here you see the emitter current is equal to base current plus collector current. This is NPN transistor. All right, here the emitter current is also equal to base current plus collector current. So the basic working of a transistor is it acts as a current regulator. A small change in current at the base can lead to a very high change in the current between the collector to emitter. It can also be used as a switch. How it can be used as a switch? If you do not apply current at the base, the transistor will be in an off stage. There would be no flow of current from collector to emitter if there is no current at the base. All right, and we'll see how transistors are used in a notebook motherboard, and what exactly is the difference between a transistor to a MOSFET. When we study the MOSFET in the later slide, we'll discuss how it is different than a transistor. These are the various coding system, the international coding system for semiconductor material, like which alphabets, like if it's written A, here as you see BC109, B means silicon. All right, and the first letter specifies the semiconductor material, and the second letter represents the type of device. So C stands for transistor. So this is audio frequency low power transistor. All right, and the subsequent letters, the characters following the first two letters from the serial numbers, from the serial number of the device. So if we check BVY13, what exactly it means? B means silicon, and another way, let's check B here means diode. All right, so this is one minute, this is a diode having variable capacitance. So BBY13 means a diode having variable capacitance. This is an international coding system, and there are two types of coding system present in the world. One is the pro electron numbering coding system, and this is the JEDC numbering coding system. In that case, the first number represents the type of the semiconductor material, the second letter and the subsequent letter. So this is 1N914, 1 stands for diode, so this is a diode, right? And this is 2N706, 2 2 means bipolar transistor, so 2N706 is a transistor. I think I'm clear with this thing. Basically there are two kind of coding system present in the world for the semiconductor devices. One we call it pro electron numbering system. In that the first letter specifies the semiconductor material, the second letter specifies the type of the devices. So BC109, B means silicon, C here is transistor. So BC109 is a low power audio frequency transistor, and BBY13, B stands for silicon, another B is a variable capacitance diode. So BBY13 is a variable capacitance diode, and this is another way of numbering system. And the first letter represent the type of the semiconductor material. So 1N914, one is diode. So this 1N94 represents a diode, and 2N706, 2 represents a bipolar transistor. So 2 represents a transistors. Alright. Alright, so now we are, I think, pretty aware with the working of transistor. Alright. So here would you find a way to test a transistor and a way to identify the various terminals of a transistor. Like if we do not know which one is emitter, base and collector, how to identify those three terminals. So for identifying those three terminals and for testing whether this transistor is okay, we must discuss a very important phenomenon in a transistor, and we will use the diode range of digital multimeter to test the transistor. But before that, we must note a very important phenomenon in a transistor. It is found that the emitter base junction poses a slightly greater forward voltage drop than collector and base. That is, in any kind of transistor, be it be PNP or NPN, the emitter base junction potential is slightly higher than collector base junction potential. Why this is? Because in any transistor, the doping concentration between emitter to base is slightly higher than the doping concentration between collector to base. So if we have any kind of transistor, be it be NPN or a PNP transistor, the voltage drop, the junction potential, that is in the diode range, what I have said earlier, in the diode range, the digital multimeter represents the junction potential drop across the PN junction. Alright, so the emitter base junction potential is always higher than the collector base junction potential for any kind of transistor. So we will use this phenomenon to identify the terminals and to check the transistor. Alright, so for any kind of transistor we will use this thing. Let's suppose this is 1, 2 and 3. So let us put the digital multimeter into a diode range, and let us connect the wire 1 to the positive side of the multimeter and the wire to the negative side, and it is giving you the value 0L. Alright, let's do the second step. Let us connect the negative side of the multimeter and the positive side to 2, and again it's giving you 0L, and let us connect to the positive 1 and 3, and it is giving 0.65 voltage is displayed on the LCD screen of the DMM, and let us connect 2 and 3, then it is giving 0.621, and if we connect the negative probe to 2 and the positive probe to 3, then it's giving you 0L. As seen, we have seen in diode when it gives 0L when it is reverse bias. Alright, when it is reverse bias. So, and you see this is between 1 and 3 it is giving 0.655, and between 2 and 3 it is giving 0.621. So we know between, as I said, the junction potential between and the emitter terminal is connected to the base, the collector terminal is connected to the base. Alright, the emitter is connected to the base and the collector is connected to the base, but never emitter and collector are connected. So the junction potential between emitter and base, as I said, the junction potential between emitter and base will always higher than the junction potential between collector and base. So between 1 and 3 this is 0.655, so it's clear that the 3 number is base because this is connected to both of them, and 1 number is emitter because I said between emitter to base there is a higher junction potential, and between collector to base this is lower junction potential. So the second number is collector. But I'm talking about junction potential, I'm not talking about resistance. In a transistor, the base emitter under a normal operation of a transistor, the base emitter are forward bias, whereas the base and collectors are reverse bias, right? In a common emitter configuration, I'll discuss about there are normal 3 types of configuration: the common emitter, common base, and the common collector, and I will discuss while tracing through the circuit, not over here, because I don't really want to make this thing to be a lot of messy, right? Here we are discussing only the testing, how we are testing the transistor. So as I said, there is a very important phenomenon in a transistor: the junction potential between emitter and a base is always higher than the junction potential between collector to base. Alright, this is due to a larger number of doping concentration between emitter to base, and there is a lesser number of doping concentration between collector to the base terminal. Alright, so this is the right way of testing any transistor. Alright, let's go to the next slide. Testing LEDs. LED is the full form of LED is a light emitting diode, and this is a diode which produces light when a current flows through it in a forward bias. So it's very easy. If you apply the multimeter across the LED, and an LED requires around 2 volts to for lighting. So if you apply the multimeter in the forward bias, then the LED should glow. Alright, and if you apply it in a reverse bias, then the LED won't glow. So this is the right testing ways of LEDs. Let's go to a linear transformer. Well, you will not find a linear transformer usually on any kind of notebook motherboard, but you will find a transformer in adapters, and you will find transformer in SMPS. And let us talk about there are 2 ways of 2 types of a transformer. One is the linear type and another is switch mode power transformer. So what exactly we measure in a transistor is we measure the resistance of the wires, right? We measure the resistance and we perform a continuity check on the primary and the secondary winding. Wherever there is a winding, we will check the resistance check, resistance and continuity test to check. Like in inductor we have done resistance and a continuity test. Similarly in a transformer we'll also do the resistance and the continuity check. And there are some ring test is also there, but we'll not focus on that ring test. You can use a ring test. There is a device for a ring test, but I think the continuity check and resistance check is quite good for checking a linear transformer. So I'm hopeful that you are understanding the various testing ways. Let's repeat it once again. For transistor, we have to check the junction potential between emitter to base and the collector to base. And in any good transistor, the junction potential between emitter to base will be always higher than the junction potential between collector to the base. Similarly, LED is like it will turn on, it will light when it is forward bias. And for transformer, you have to check the resistance and the continuity check for this. All right. Okay, so till now we have discussed the various testing ways for resistors, capacitors, inductors, diode and transistors. But here in the last phase of this session, I'm going to cover the MOSFETs, which is a very important component present on a notebook motherboard. And if you understand the working of a transistor and a MOSFET, you are clear with everything on a notebook motherboard. You can really diagnose that notebook motherboard if you understand this thing. So testing a MOSFET and testing the transistor and knowing the working of a transistor and a MOSFET is the key, is the very key element in repairing. Let's discuss what exactly is the difference between a transistor and a MOSFET. As we see in this diagram, a transistor is also a three-terminal device. What are those three terminals? Base, collector and emitter. Whereas what are those three terminals for a MOSFET? MOSFET stands for metal oxide semiconductor field effect transistor, whereas BJT is a bipolar junction transistor. So in a MOSFET, those three terminals are called as gate, drain and source. So this is very similar. This is also three terminal devices. This is also very three terminal devices. But what exactly is the difference? In the transistor, we always talk of control current. The current at the base controls the current flow between collector and emitter. Whereas in MOSFET, the voltage difference between gate and source governs the flow of current between drain to source. Whether the current will move through drain to source or source to drain is dependent on the voltage difference between gate to source. So in other words, we can say a transistor is a current control device, whereas a MOSFET is a voltage control device. So wherever we find transistor, we have to always talk about current, never voltage, whereas in MOSFET we have always talk about voltage between gate and source. So there are two types of MOSFETs. One is depletion type, another is enhancement type. But in a notebook motherboard or a desktop motherboard, usually we have enhancement type motherboard, and there are two types of enhancement type motherboard. One is N channel and P channel, and we'll see the differences between the N channel and the P channel. Let's go to the next slide. And in this slide, this is an N channel enhancement type MOSFET. In an N channel enhancement type MOSFET, when I mean MOSFET, I mean enhancement type. So from now on, I'll use only MOSFET, but I am referring to an enhancement type MOSFET. Okay. So in a MOSFET, in an N channel MOSFET, we have two N type doped region, N type doped region, and we have a P type substrate, and drain is here, gate is here, and source is here, and all those three terminals are not internally connected. See the difference. In a transistor, the collector and emitter are connected to the base, whereas in a MOSFET, all these three terminals are not internally connected. But when you connect a battery between gate and source, give positive supply to the gate and a negative supply to the source, in an N channel MOSFET, a current will flow from drain to source. Okay, a current will flow from drain to source. So what is the important point we have to note in an N channel MOSFET? In an N channel MOSFET, if VGS is positive, VGS is positive means voltage at gate is positive than voltage at source, then a current will flow from drain to source, and a current will flow from drain to source. That means in an N channel MOSFET, the input is connected to the drain and the output is connected to the source, and a current will flow from drain to source only when VGS is positive. Voltage at gate is higher than voltage at source. Okay. Similarly, for a P channel MOSFET, we have two P type doped region and N type substrate, and a current will flow from P channel MOSFET from source to drain, opposite to N channel MOSFET. In the N channel MOSFET, current flows from drain to source when VGS is positive, whereas in P channel MOSFET, when VGS is negative or some specified value, that specified value is written in the data sheet. You'll always see VGS written in a data sheet. So if VGS is negative in a P channel MOSFET, then current will move from source to drain. That means the input is connected to the source and the output is connected to the drain. I'm putting a stress on these 2 points VGS, because this is very important. If you're not getting it, let's revise it again. In an N-channel MOSFET, a current will move from drain to source only when voltage at gate is higher than voltage at source. VGS is positive. Alright, when the input is connected to the drain and the output is connected to the source. Whereas in a P-channel MOSFET, a current will move from source to drain only when VGS is negative. In case when input is connected to the source, not vice versa. We'll also look what happens when the input is not connected to the drain in N-channel MOSFET. When input is connected to the source, what happens in that case? You see, the MOSFET used in notebook motherboard, they have an internal diode present. This diode is called damper diode, alright? And we are talking about how we identify which one is an N-channel MOSFET and which one is a P-channel MOSFET. In an N-channel MOSFET, this arrow is inside, alright? Whereas in P-channel MOSFET, this arrow will be outside, alright? So we have to identify how an N-channel MOSFET, which one is an N-channel MOSFET and which one is a P-channel MOSFET. In an N-channel MOSFET, the arrow will be inside, whereas see here, the arrow should be inside, and in a P-channel MOSFET, the arrow should be outside, pointing outside, alright? And normally the MOSFET used in a notebook motherboard has a damper diode, and this direction is opposite. You know, as I said, in an N-channel MOSFET, the current flows from drain to source when VGS is positive, but here diode is connected from, you see, source to drain. Alright, so this is connected opposite side, and here this diode has an application. What is the application of this diode? The question is, what is the application of this diode? As I said, a N-channel MOSFET is normally used when the input is connected to the drain and the output is connected to the source, and VGS is greater than 0, then current will flow from drain to source. But let us consider a case in which the input is connected to the source and the output is connected to the drain. In that case, this MOSFET will allow the flow of current through this diode, and in that case this MOSFET is not used as a MOSFET but rather than as a diode. But the question again is, why can't we replace this MOSFET by a normal diode? We cannot replace this MOSFET by a normal diode because across a MOSFET the voltage drop is very less, and across a diode there is a 0.6 voltage drop across a diode. So when we want to use this MOSFET as a diode, then the input is connected to the source and the output is connected to the drain. But the normal operation of a diode is, the normal operation of an N-channel MOSFET is the input is connected to the drain and the output is connected to the source. Similarly, you can apply it for a P-channel MOSFET. Okay, in a P-channel MOSFET, we know the current will flow from source to drain, that is, the source is the input, the drain is the output, and when VGS is less than 0, then a current will flow from source to drain. But here there is a damper diode which is opposite to the direction, and this is used when the input is connected to the drain and the output is connected to the source. In that case it will allow a flow of current, and in that case it is used just as a damper diode. And again I said, we cannot replace this by a normal diode because across a normal diode we have a voltage drop, and we cannot afford to have a voltage drop because I said in an electronic PCB circuit, what is fixed? Voltage is fixed at each point. Okay, what is fixed? Voltage is fixed at each point. So in a P channel MOSFET, I talk, in a P channel MOSFET, current will flow from source to drain. This should be source, this is wrong. Source to drain only when VGS is negative. VGS is negative means voltage at gate is less than voltage at source. Okay. And let's talk about, this is the representation of MOSFETs. As I said, if the arrow is pointing in, then that means an N channel MOSFET, and if the arrow is pointing outside, it means a P channel MOSFET. Alright, so let us consider an example how the N channel MOSFET operates. Suppose there is a 12 volt present on a drain of an N channel MOSFET. This is the arrow is inside, so it's a N channel MOSFET. And let's suppose there is a 0 volt as the gate. Will current flow? Will a current will flow through this MOSFET? Tell me. Will a current will flow through this MOSFET? As I said, in an N channel MOSFET, for a current to move from drain to source, the VGS should be positive. Here, the if this switch is closed, if MOSFET is basically used as switch, so if this switch is closed, then this 12 volt will come over here. Okay, so what we want is this switch to be closed. That means the voltage at the source would be eventually be 12 volt when this switch is closed. So for VGS to be greater than 0, we have to have voltage more than 12 volt. Okay, so if we have a voltage between 15 to 18 volt, then this MOSFET is turned on. Whereas if there is a less voltage, if there is a less voltage at gate, suppose the voltage at gate is 11 volt, then this MOSFET will remain turned off. The switch will remain as turned off. The current will not flow. This voltage will not appear over here, because if this MOSFET get turned on, the switch is closed and this point and this point is connected. But here there is 0 volt. So we have to apply a volt greater than 12 volt and a specified value. That means if we apply a voltage between 15 to 18 volt, then this MOSFET will get turned on. Okay. Let us check the schematic diagram to understand it. And I've opened the DB2000 page, and let's move to the 46 number page. Here you see the adapter is connected to the DC jack. Okay, so voltage is coming over here. This point is connected to the DC jack, so the adapter volt would be here. And as you see, this is 4407. The arrow is pointing outside, so this is a P channel MOSFET. And also through the numbering, you can also decide whether it's a P channel or N channel. If the last two digits are an odd number, then this is a P channel, and if the last two digit number are even number, then generally this is a N channel. So 4407, the last two digits are odd, so this is a P channel. As I said, in a P channel MOSFET, the current will flow from source to drain. So here you see, source is connected to the input side and the drain is connected to the output side. When the current will flow from source to drain, when VGS is negative. VGS is negative means voltage at gate should be less than voltage at source. At the source, this adapter voltage is coming, so here 18 volt, but the gate is grounded, so VGS is negative. That means this MOSFET switch will close, turn on, so the current will move from source to drain. You got it? I said in a P channel MOSFET, the current will move from source to drain only when VGS is negative. At this source, here is 18 volt, gate is ground, so V gate is less than V source, so it will allow the flow of current. Alright, you got me? If there is any confusion in this one, we have to revise it once again. Let's note down the important point. The important point I said is, in an n-channel MOSFET, the VGS should be greater than 0 or some specified value. The current will move from drain to source. Whereas in a p-channel MOSFET, the VGS should be negative than 0 and the current will move from source to drain. This is a normal operation of the MOSFET. But if a n-channel MOSFET, if the input is not connected to the drain, if the input is connected to the source, then the current will move through this damper diode. And in that case, this MOSFET will only act as a diode. So in that case, we do not have to think about gate, because in that case, this MOSFET is operating as a diode. Now let us go into the working of regulators. Okay, so now we are going to understand the working of regulators. Why I am discussing regulator is because regulator is at the center of power management of any electronic device. As we know, in an electronic device, the source, the starting point is always at higher voltage, whereas the ending point is always at lower voltage. Like in the case of notebook motherboard, the higher point, that is at the DC jack, we have the adapter voltage, whereas at the ending point, that is at the CPU, we have the least voltages. And how this voltage conversion takes place, it is the work of the various regulators present on a notebook motherboard to convert the adapter voltage into the lesser voltages required by component like south bridge, north bridge and the CPU, right? So this is very fundamental which I am speaking. There is always a source and a sink. The source in the notebook motherboard is DC jack, whereas the sink is processor. Processor requires the least voltage, but it requires the highest current, whereas the DC jack, we have the highest voltages and the least current. And the job of regulator is to generate the various voltages from one fixed voltages as required by the electronic device. Alright, and there are various type of regulator: buck regulators, boost regulator. Buck means a step down, boost means step up. So normally in a notebook motherboard, we'll always find a step down regulator. That means we try to generate a less voltages from a high input voltages. This is a basic block diagram of a regulator. In a regulator, you will find two switch. And what are those two switch? Two switch are basically two MOSFETs present outside, and we have one IC and we have two MOSFETs, one inductor and one capacitor. You see in the next slide, this is the regulator IC, the two switch, the top gate MOSFET, bottom gate MOSFET, and the inductor and the capacitor. So before analyzing this slide, let's move to the previous slide. This is a very basic block diagram of a regulator. So in the regulator, we have the input voltages, two switch and one inductor, one capacitor, and this is Vout. So what is the physics behind generating a less voltages from a high voltage, or of a high voltages from a less voltage? Let's understand this. Let us close this switch S1 and let's for a time while open this S2, S1, S2. Okay, when we close this switch S1, current will move across this inductor, but as we know, an inductor opposes the flow of current, so the rise of current would be slowly. Okay, so when the current reaches at this point, we open this switch and we close this switch. So at this point, the voltage seems to be 0, but as we know, an inductor opposes the flow of current, so immediately this current will not go to 0, it will go slowly. So when it reaches here, we again close it over here and the current will increase, and we again open this and close this, so will it reduce like this. So current will move like this. Okay, and if we analyze this circuit, then we will find out that Vout by V in is equal to delta TS1. Delta TS1 is the time for which this switch S1 is closed. divided by total time. So if you want to get a higher V out, then this delta TS1 should be higher, and if you want to get a less voltage, then this delta TS1 should be lower. So if you want to check, if you check logic over here with a digital multimeter in case of a CPU regulator, you will get a very less high logic. Less high logic means the upper gate MOSFET will be turned on for a very few time, and the bottom gate MOSFET will turn on for a much time, because I said this is delta S1 represents top gate MOSFET and delta S2 represents the bottom gate MOSFET. So consider two regulators, one regulator for IO and another regulator for a CPU. As you know, a CPU requires a less voltages, so the time for which this S1, time for which this MOSFET will get closed would be less as compared in a case of a 3.35 volt regulator IC. In that case, this S1 would be more. So you'll get a higher logic, a high logic at the 3.35 volt regulator IC as compared to the CPU core regulator IC. And this is a block diagram of a regulator. A common regulator have a IC, regulator IC, alright, 3.35 volt regulator IC, 0.5 the core voltage regulator IC, VRM, we call it voltage regulator module, the core VRM, and two MOSFET. This is top gate MOSFET. Top gate MOSFET represents switch S1, the bottom gate MOSFET represents S2. Okay, and this switch S1 and S2 are turned on with a signal from the regulator. This is DH. DH means drive high. So this DH is connected to the gate of this MOSFET, and this DL is connected to the gate of this lower MOSFET, the bottom gate MOSFET. And this turning on and turning off is controlled by this IC. Okay, turning on and turning off of these MOSFETs are controlled by this IC, and the feedback between the common is connected the inductor, and a feedback is given to the regulator IC. Feedback is given so as to check whether we have got the right output at this point or not, so that with the feedback the regulator will drive this signal at drive high and drive low to generate the required output voltages. So you got how the output is generated. V out by V in is delta TS1 by delta TS1 plus delta TS2. This is also called duty cycle. Okay, and this is a dual in voltage regulator. We are getting two outputs from a single voltage regulators. From a single voltage regulator we have got two outputs. No. Okay, so now comes the most important point of the today's class, and the final point that we are going to discuss in the today's class is testing a MOSFET. There are various confusion in the market to how to exactly test a MOSFET. We can test, there are two procedures. We can test the MOSFET if we want to test, as I said, in notebook motherboard, the MOSFET which are used, they have an internal damper diode, but this is not true for all the MOSFET, because not all the MOSFET have an internal damper diode. Okay, but for a notebook motherboard we can test the internal damper diode. As I said, in an N channel MOSFET we have an internal damper diode. Similarly, in a P channel MOSFET we have an internal damper diode, and if you put the positive probe at the source and the negative probe to the drain, and in the diode range it gives you value of 0.6 to 0.7, and if it's reverse it gives you 0L, then this MOSFET is good. We are basically testing the damper diode. Okay, this is also one way. Similarly, you can check here also. If you put the positive probe onto the drain and the negative probe on the source, and we are in the diode range, it gives you 0.6, values between 0.5 to 0.6, then this diode is good. This damper diode is good. That means this MOSFET is good. This is one way. But sometimes this test fails, so we have to have another kind of test, and this is, we call it call it as a diode under we call it diode under test. This is similar to the previous test, but we have to use 4 steps over here. What are the 4 steps? We'll first connect the, will not think about what kind of MOSFET it is, right? We do not think what kind of MOSFET, whether it's N channel MOSFET or P channel MOSFET. We'll just connect the source of the MOSFET to the negative terminal, and we'll connect the positive terminal to the gate, okay, onto the gate, and we'll now move the positive terminal to the drain. Then it will give you a low reading, because here the MOSFET internal capacitance in the gate has been charged up and the device is turned on, okay. So first step is we have to connect the negative terminal to the source, and then connect the positive terminal to the gate, and then move the positive terminal to the source. It will give you low reading, and then we have to discharge this capacitor. If you discharge this capacitor, then a high reading would come to the multimeter. This is the right step for testing MOSFET, and we'll have some videos also. I will be giving, after this class, I will be having some videos of testing all the electronic components which we have discussed in this class, and I hope you understood this class. And in the next class I will be going into the schematic, how to understand the various schematic diagram and understanding the concept. But be aware, note my points, note at least 2 points: the points mentioned about transistor and the points mentioned about MOSFET, because these are the 2 concepts which are used extensively in a notebook motherboard. And for today's class, this is over. And again, I would say you, if you have any doubts in my classes, please take a note and email me. We can discuss it in the next class. Good afternoon everybody, and in this class I'm going to explain you the use of DC power supply for sorting problems. Use of DC power supply is very important in laptop chip level repair, as it is one of the device which solves the problem of sorting. And this is you can tell that this is kind of magical device, and by DC power supply we can find this sorting very easily. And the kind of DC power supply which has to be used should be 30 volts 5 ampere, because as you know, in a laptop motherboard the maximum voltage is DC bat out, and it's around 19 volt, and the maximum current taken is by CPU. So to find sorting, we have to have a fixed kind of external supply, because you know, in sorting the voltage would be shown 0. That is, you get a short path in the circuit where current can flow freely and the voltage would be shown 0. So you cannot check which device has got sorted. So you must have some kind of external regulated supply to check the sorting. And I would be showing you one videos which is made by my colleague for finding out the sorting problems. So hope you will enjoy it, and if you have any problems we can discuss it after this class. Okay.
Hello friends, today I'll show you how to use DC power supply machine in repairing. Here I have one faulty motherboard which is in a dead condition. I'll show you with DC power supply. This DC power supply you use as a adapter also. That's why I have a jack, different jacks. I put this here. You see 19 volts coming, and here when I turn on this board, not get it on. Now what we need to check, first we need to check our adapter volts come into the laptop or not. That's why we need to check voltages, adapter volts, it's coming or not. Now here I'll check adapter volts. Look, here we have adapter boards, and when we check other side inside motherboard, like the top gate MOSFET, TG MOSFET, here we not get any adapter volts. Look, no voltages, no voltages. Here also you see no adapter volts, no adapter volts. Now when I check over here, here I will get adapter volts, but here no voltages. Now what we need to do, first I will remove this and set multimeter on continuity mode. First we need to check shorting. Now I'll check here. Yeah, look at the value. Here we get 0 value. Yeah, this is the shorting. Now when I check, everywhere I get shorting. Every component give beep. Look, everywhere shorting inside the motherboard. How do we know where is the actual fault inside the motherboard? Now for this fault, this kind of faults, we solve with this DC power supply. Now what we need to do, we place one jumper to this MOSFET, because this MOSFET provide adapter volt to inside the motherboard. That's why here I'll put one jumper over here. I soldered this. Over here, because I get shorting over here also, and one round. Okay, now I connect this cable into the DC power supply. Okay, now completed. Now I'll start. Look, shorting present in this board. Here I'll get red LED on. Status is red LED, it means motherboard short, but we need to know where is the actual component fault. Now here what we do, increase ampere slowly, and then we check heat. Where is the which component going to be heat? Like MOSFETs, you check everywhere like this. For heating, no. No heating, no. Yeah, here I'll feel little bit heat. Now I increase ampere. Yes. Here this capacitor generate heat. Now I'll remove this capacitor first, then after I'll check it again, shorting gone or not. Now I remove this capacitor. Now I'll check again for shorting, it's gone or not. Yeah, shorting not present, shorting, I think shorting gone, no beat. Yeah, now I'll check back again after removing this capacitor, faulty capacitor. Now I'll check here. Yes, it's gone. Now our motherboard is okay. Now what we need to do again, here I'll put adapter for testing. And here I'll check. Our adapter board is coming or not. No adapter boards coming. Now I place here one capacitor back again. Because here one capacitor faulty, that's why here we get shorting over here. When I remove faulty capacitor, shorting gone. Now I place one capacitor over here. Okay, now here we check. Okay, and check back again. Yeah, it's turned on. Now with this power supply, DC power supply machine, we check where is the actual component faulty to do like this job. Thank you.
Today in this class I'm going to cover the digital circuit framework. Why I've chosen this digital circuit framework topic is basically to understand the very concepts behind the working of digital ICs present on laptop motherboard. In later stages I'll tell you that every digital IC requires three things, that is supply, reset and clock. So I'll get to the point why actually they require three things, the supply, reset and clock. And I'll also cover some of the important electronic digital components like op-amp and comparator, which are present everywhere on laptop motherboard. So to understand the schematic at the deepest level, we must understand each and every components and its working. So in this class I would cover all those things, and I'll also cover the basics of laptop motherboard, and I'll also go into details like how the schematic or these Gerber file are read and they are viewed in the PCB layer. Though there are many things which are IP protected, that means they are intellectual property. So every information whichever I am giving is just to impart knowledge. I am not imparting any knowledge which is against the intellectual property rights of companies. So in this class we are going to cover the digital circuit framework, and let's start with the class. Op-amp. Op-amp, the full form of op-amp is operational amplifier, and this is one of the components which is commonly present on all kind of electronic devices, and this is represented by a triangle, and it accepts two input, inverting input and non-inverting input, and it gives one output. Non-inverting input is at plus and inverting input is at minus. So what actually it does is, this operational amplifier, it amplifies the difference between these two inputs and its output, and it amplifies the difference and give output at this terminal. So if the input at this V plus terminal is greater than this V in minus terminal, then the output would be a positive amplified version of this difference. And if this V in, that is the voltage at this negative terminal, is greater than the voltage at this positive terminal, then the output would be a negative voltages. How much negative? It would be an amplified version of this difference. Alright, and there are two important characteristics of this op-amp. The input impedance is high and the output impedance is less. The output impedance is less, that means it will drive the output signal very easily, and if input impedance is high, that means it will not accept any current, it will not load the input side, right? It will not load the input circuit, whereas it will just drive the signal easily to the output. So these are the two important characteristics of an operational amplifier, and we call operational amplifier as an op-amp. Comparator circuit. Comparator is one special case of operational amplifier, and what it does is it outputs either 1 or 0. If the voltage applied at plus, that is V plus, is V in, if V in is greater than V reference, then it will drive out 1, and if it's less than V reference, then it will drive out 0. So what is the purpose of this comparator circuit? This comparator circuit are often used to check whether an input has reached its predetermined values. This is very important. I'm again repeating why this comparator is used. This comparator is commonly used to check whether the input voltage had reached a predetermined value, and you will find this comparator circuit to be present often in V in detection. V in detection, you will find this comparator like in almost all schematic diagram, and so I have explained here the comparators. All right. Now comes analog versus digital. What is difference? We always talk of this is analog, this is digital, but do we understand it properly? See, there are two kind of circuit. One is analog circuit and another is digital circuit. An analog circuit, this operates on a continuous signal. Here in this graph you can see these physical quantities like voltage, current and time, they changes continuously. There is no break between there is no break, they're all continuous. Whereas in this graph you can see they're all discrete, right? They're all discrete. So if a circuit that works on continuous signal, it is called an analog circuit, and if a circuit, if it works on a discrete signals, it's called a digital circuit. And we know our computer, our processor, it works digitally. So what we need, so but the voltage, current, they're all continuous, they're all analog. So we need some kind of device which can convert this analog to digital. And an analog digital converter, that is analog to digital converter, it samples the analog signal. It will sample the analog signal at predetermined time interval, and it will convert into a binary number, right? It will convert into a binary number, but some information would be lost in while converting an analog to digital. But if we reduce this time, then that probability would be less. So we'll see in the schematic diagram, we have an analog to digital converter present inside. You can see a battery charger or inside an IO controller, because you will see at the pins of IO, it will receive an analog voltage, it will receive an analog current, but inside the IO controller there is an embedded controller, and that embedded controller is a microcontroller. It works digitally, so it requires digital inputs. So we must have an analog to digital converter inside an IO controller, inside a battery charger IC. So that's why I'm introducing this concept of analog to digital conversion. All right, so let's go to the next slide. What exactly are digital ICs? See, digital ICs are of exactly two types. One is they are made of two types. One is made of bipolar junction transistor, and another are made of the MOSFET. That is, MOSFET is metal oxide semiconductor field effect transistor. As we have studied in our previous class, what are the differences between a transistor and a MOSFET? So I won't go into that detail, but I'll just tell you that digital ICs are of two types. One is BJT, the IC which are using BJT inside it, and another one which is using the MOSFETs inside it. And the IC like microcomputer, they're all ICs, memory, they're all ICs, standard logic, they're all ICs. So you'll find ICs everywhere. IO controller is an IC, PCH is an IC, all are digital ICs. Alright, and combinational logic. This is very important, but I don't think this would be much important for a person who is into repairing, but if you want to understand everything very smoothly, you must understand what is a combinational logic. As you'll find at some kind of in laptop motherboard schematic, you'll find AND gate, you'll find NOR gate, and these are all combinational logic. What exactly is a combinational logic? Combinational logic refers to a digital circuitry whose output is a function of present input signals. This seems to be very hard to understand it, but let me simplify it. What exactly in a combinational circuit means? The output, it depends only on its input. It doesn't depend on its previous state, right? It doesn't depend on its previous state. It just depends on its input. And this diagram is an example of a multiplexer. What exactly this multiplexer will do? It will output the input. It will output one input out of these four according to the conditions. Okay, according to the conditions. So this is a multiplexer, a kind of combinational logic. So in combinational logic, the output depends only in its input. It doesn't depend on its previous state, right? It doesn't depend on its previous state. So it means they do not have a memory. They do not have a memory. Whereas sequential logic is not determined solely by present inputs rather than an internal memory circuit, right? Internal memory circuit. So this is what is sequential logic circuit. As spoken, this circuit consists of memory and the output depends on its present input as well as the previous state, right? As well as the previous state. So we have many kind of sequential logic, the RS flip-flop, the D flip-flop, and I'm not going into much detail about this. This will take another 20 hours to explain all these things. 20 hours to explain all these flip-flops and everything. But the students who are very much interested to learn about these flip-flops, and this is very vast actually. You can calculate the state and you can represent this sequential logic with combinational circuit, and there are more to it. So but I'm not we're not concerned with the sequential logic circuit too much here, but just you need to understand that the sequential logic circuit, the output depends on the inputs and as well as the previous state, right? And I'll also tell where these are used. When we are studying schematics, I'll tell you where these are used. Okay, this is an explanation of sequential circuit, and I'm not going to the details of explanation of the sequential circuit because this slide is basically the slide which I have taken in my when I taken the lecture in the engineering first year at one of the private engineering college. I take the electronics classes over there. So this presentation is basically of that class. So let's skip this portion, and if you are interested, you can personally email me to understand this is sequential circuit. Yeah, this is very important. The need for a clock circuit. You can see everywhere on a scheme, everywhere on the laptop motherboard, we tell there is a requirement of a clock generator. But do we really understand why a clock circuit is required? Why exactly a clock is required? We must understand one thing, that why a clock is required. A clock is required because in combinational circuit, and you will find in laptop motherboard, almost every portion is combinational logic. In laptop motherboard, it doesn't depend on the previous state. So the laptop motherboard is purely a combinational circuit, except few, and we'll discuss what are those few which are in sequential logic. So the entire laptop motherboard is a combinational circuit. All right. So why do we require a clock circuit? We require a clock circuit because sometime in combinational circuit it will output a certain unwanted signals, and as a result of actually delay in signal transmission. You see, this is entire combinational circuit, all right, and in between them are flip-flops. In between are flip-flops. It's same like a laptop motherboard. So if there is a delay in signal, this combinational circuit might generate a glitch, we call error or glitch. So we need a clocked circuitry to produce a right kind of output. Okay, so clock is required to produce a right kind of output, not to produce error. So we must we should just note one thing, that a clock circuit is required to produce a right kind of output, not error. Let's go to the next slide. And yes, microcontroller. Actually, why I have used this microcontroller is because inside a laptop motherboard we have many kind of microcontroller, and out of this the IO controller is one very important microcontroller. So what exactly a microcontroller is? A microcontroller, inside a microcontroller you will find a CPU, inside a microcontroller you'll find a memory, and inside a microcontroller you'll find peripheral devices. So this is a kind of all-in-one devices. Whereas on a laptop motherboard, inside a CPU, it doesn't has a memory inside it. You have a RAM, right? It doesn't have a memory inside. And the dual core boards, it doesn't have a clock generator also. But a microcontroller, it has a processor, it has a memory, and it has a peripheral functions inside it. CPU, you can call CPU a kind of microcontroller. If we call there are internal registers inside CPU to store data, but as a true example of a microcontroller is an IO controller. So what is inside a microcontroller? In a microcontroller we have a CPU, memory, and a peripheral functions, and there are input devices connected to those microcontroller, and that will output, and output devices are connected like LEDs. In case of laptop motherboard we have like on-off LEDs, charging LEDs, battery LEDs, those are all connected with IO. So IO, the input output controller present on a notebook motherboard, is a very good example of a microcontroller. Now let's go to the next slide. And CPU, we call CPU the thinker. Why? Because this control and this compute data. It actually controls and compute data, and inside a basic, this is a basic layout or a basic block diagram of a CPU. So inside a CPU you have a program counter, you have an instruction decoder, we have an ALU, that is arithmetic and logic unit, and we have the CPU internal registers. All right, so this is CPU, the thinker. All right, so what are inside a CPU? Just remember that inside a CPU you have a program counter. What is the function of program counter? It holds the address of next instruction to be executed. Next instruction to be executed, and it has instruction decoder, it has an arithmetic and logic unit, and it has a CPU internal registers which store the calculated datas. So I think I'm clear till this point. Okay, why we use a microcontroller? Now the question is, why actually we use a microcontroller? Let's understand these two images. In the first image we have a switch, we have a resistor, and we have a LED, light emitting diode, and we have a battery. If we turn on the switch, then a current will flow and the LED will glow. But if we want some kind of some twist to this application, like we want that after 10 minutes, after pressing this switch, the LED should turn on after 10 minutes, then we require some kind of a microcontroller, and this same work can be done through this microcontroller. Okay, this microcontroller is having 4 pins. All right, these are 2 input pins and these are 2 output pins. All right, so we can, if we require some kind of logic here, what is the logic here? Our logic is, we require that after pressing the switch, after some certain minutes, we want these LEDs to turn on, then we require some logic. So where logic is there, we require a microcontroller. Alright, where logic is there, we require a microcontroller. We can represent that same circuit through an ordinary circuit, but there won't be any logic. And we'll see where this microcontroller is used. This microcontrollers you can find in also voltage regulator. This kind of MCU you can also find it in voltage regulator. It generates signals. It generates the voltage regulator. It generates signals at the gate of the MOSFET connected, as we have seen in the previous lectures. What is voltage regulator? Voltage regulator is an IC with two MOSFETs connected. So the signal generated by the voltage regulator at the gate, it varies, right? It varies. So there is some logic involved. So anywhere you have logic, you require MCU, you require a digital IC. So I think I'm very much clear. I'm trying to relate everything which I have spoken. There is nothing in electronics which can't be explained. We should not assume anything. We should not assume anything in electronics. Everything is man-made, and anything that is man-made can be explained properly. Okay, let's go to the next slide. Three things. Yes, this is actually the crux why I started with this class, why I started with this digital circuit framework. Any digital circuit, it requires three things: supply, clock, and reset. We'll see. This is a kind of digital IC, okay? So it will require some kind of power, power. Any digital IC, it requires power. Until you give power, it won't run, it won't operate. So you see, these are power pins. You see, these are power pins. They are all connected to power, right? They are all connected to power. So the first important thing we must understand is, any electronic device, any electronic IC, it requires three things to function: supply, reset, and clock. Supply, you understand, power. This is basically a generator. We call it generator, power circuitry. Now let's go to the next slide. Oscillator, right? As we have seen, why a microcontroller basically requires the clock, as we have studied why it requires clock. So you require some kind of clock signal, so we require oscillator. As you can see, in IO controller, a crystal is connected with an IO controller. Similarly, a crystal is connected with an ICH, and you have a clock generator where a crystal is connected with this clock generator. Okay, but nowadays the clock generator are present inside PCH, and you will find inside an besides I, you will find a crystal that generates clock signal. So any digital circuit requires three things: supply, reset, and clock. Now reset circuit. This is the very important signal which is required. We call it reset signal. So I'll basically not go into that detail, but let me just explain it. It takes a short time after MCU that any microcontroller power. Actually, what happened when you give power to the microcontroller, or when you insert adapter, and when power reaches to each component in a laptop motherboard, it requires some time for the internal circuitry of those devices to stabilize. And during that interval, we cannot expect a CPU to perform some kind of activity. So during that problem, we require the reset signal to be low, that is active low. So this is reset signal. Okay, so any electronic device, it requires three things: supply, clock, and reset. The reset signal should have to be low during the period when the internal power circuitry of all the digital ICs stabilize, and after some time this reset signal will go high. I'll speak about this when we are going to discuss this CPU reset signal. CPU reset signal, this is a very important signal present on a laptop motherboard. But why I have referred is, Why reset is required? A reset is required because the internal power circuitry of digital IC requires sometimes to stabilize. It requires some time to stabilize. So during that point, we need some kind of signal which can let the outside world that no, I'm working, I'm not yet ready, right? You can call reset signal to be a ready signal, all right? So I'm not ready. So during that point, the reset signal would be low, and after it gets ready, the reset signal would be high. So there are three important things required for a digital IC: supply, reset, and clock. And in the next class, I'm going to use all these concepts. So please get these things revised again and again, because I'm using these concepts later on, and I'm not going to explain these concepts later on. Alright, and again, if you have any kind of query, just email me. Hope you know all of my email IDs, and you can just email your queries. And we are going to use this concept in understanding the schematic diagrams. I'm a little bit slow in explaining things, but I want the entire things to be connected so that you don't have any confusion. Alright? Okay, till now in this class we have covered till the digital circuit framework, and now after completion of this digital circuit framework, I will starting with the basic structure of a notebook motherboard. And after covering this class, we'll directly enter into explaining the schematic diagram. And why I've taken so much of time is because I need to cover the basic background to understand the schematic diagram. And so this is very important. These classes are very important because I will be referring all those concepts discussed here, and while explaining the schematic and while the fault-wise analysis. So let's start with the next topic, that is the notebook structure. And this is the agenda of this topic, that is we'll study the system overview, key components, system memory and VGA, IO interface, AC adapter and battery, and the Allegro view application developed by Cadence, which is one of the very important software for viewing the .brd files. And these are actually IP protected things, but I will referring those things just for a knowledge sake. Let's go to the topic, that is system overview. And system, we have system block diagram, as I've already discussed this in the very first class. To understand any electronic devices, we must understand its schematic diagram, and the very first page of a schematic diagram explains the block diagram. So the block diagram is basically a simplified version of any electronic devices, where all the important devices or components present on that electronic device is represented. And here we are referring to laptop motherboard. So in the laptop motherboard, we have a sample block diagram. Here this is Johanna is an Intel terminology for Core 2 Duo processor. This is Calistoga. This is the North Breeze, and this is ICH7 South Breeze. The RAM slots are connected. The graphic chip is connected. The KBC, this is IO controller. We have a crystal connected with the South Breeze. We have a crystal connected with the IO controller. And this is LPC bus, DMI bus, host bus. We already discussed in the very first class. Just a rough overview with visual diagram, so that I want everybody to understand it visually on the notebook motherboard. What is North Breeze, what is South Breeze, what is IO controller. To show it pictorially, I've used this class. Let's go to the next class, and this is the component size. So as you know, a notebook motherboard has a component on both sides of the board, whereas a desktop motherboard has a component only on one side of the board. So this is the component side, and in the component side we call it the component side, the side which is having processor socket, we call it component side. This is CPU, this is North Breeze, this is graphic chip, this is South Breeze, this is the card bus controller, and these are the DIMM slot, the RAM slot, okay, and this is the LAN chip, okay. Next go to the second end, this is the solder side. So a notebook motherboard has two sides, one is component side, another is solder side. The component side is the side where the CPU socket is present, and the other side is called solder side. So on the solder side you will see the VGA bracket, that is for giving that VGA bracket, alright. of, if we apply a heat sink over there, we need the brackets. This is the CPU brackets, okay, and the embedded controller. Normally an embedded controller is found to be on solder side, right, whereas a north bridge or south bridge is found to be on the component side. And you know, the BIOS chip is connected to the IO controllers, and this is the card reader. Okay, so these are the key components of a notebook motherboard. The CPU, here in this schematic I am showing you the Core 2 Duo, and this is Iohana, Intel quality Iohana. This is Intel terminology, and the north bridge, and the north bridge used over here is 945GM. If you go into the exact chip number, then it would start by ALE82965, AC82945, like this the ICs. South bridge is 82801 GBM, FBM, DBM, IBM, it will like that. Okay, this is VGA, the ATI graphic chip is used over here, and this is keyboard and power management controller, which we also call it the IO controller. So the IO controller used over here is PC97551, and this is flash ROM. This is a BIOS chip. CPU, the CPU which is used over here is Core 2 Duo, and the Core 2 Duo processors are normally set into 479 PGA socket. Okay, PGA socket. This is the 479 PGA socket. You will find this socket like this. This is CPU socket. I think all of my students are aware with this, but even for you can say it for revision purpose, I'm taking this class. This is the CPU package. This is the top view of a CPU, and this is the bottom view of the CPU. On the bottom side you see the pins, and on the top side you see this is a core. And the north bridge, as you say, as we already studied in the class 1, in north bridge consists of